So in this course, we don't cover a specific architecture down to some gory level of detail. Instead, so we scratch the surface of more conceptual solutions to how you build architectures. Still, I'm going to show you a few slides about x86, where it's coming from, and also give a brief introduction to its vector instructions. And there's more information in the lab preparation material about what the vector instructions are in x86 and how to use them. So looking back at archaeology, the x86 has lots of relatives going all the way back to 1974. So back then, the 8080 controller was a 6,000 transistor, 2 megahertz, 8-bit design. And then that idea and that basic instruction set has been carried forward with modifications, small modifications, up to 8086, which was really the first real incarnation of the x86 instruction set. It's a 16-bit ALU, and this is what was used when the PC was first introduced in the 80s. So it's, of course, was a very important chip. The 186 was not that important. It was more or less a flop, not meaning floating point operation, but there was no big hit. 286 was a much larger hit. It was used in the sort of second generation of PCs and AT. Still 100,000 transistors, so it's it's huge improvement. But walking down here from generation to generation, you can see the number of transistors has steadily been growing, and we passed 1 million transistors way before the turn of the century. You can also see what kind of features have been introduced for each generation. So we moved up to a 32-bit instruction set in 1985. We introduced instruction and data caches on chip, as well as floating point units. Pentium 1993 was the first one to introduce superscalar implementations. Pentium Pro, 4 years later, introduced out-of-order implementations, and here we have this three-way superscalar. And in 2001, the Pentium 4, you actually managed to get the L2 cache on chip as well. So it's been a tremendous development in this architecture. These architectures of 8086 had some number of registers. Many of them had very much a sort of special purpose goal in life. And as I told you before, this instruction set was most often used by programmers or very often used by programmers to write their applications in assembler. And that's why you made the programming much easier with these special purpose registers that were also were tied into some fairly complex instructions in the instruction set itself. So, if you look at instructions that are more general purpose than others, that would be these 4 registers. Even though they have special names, they don't have that much kind of hardware functionality tied into them. Then you have like stack pointer and base pointer and source index and destination index. These are more tied into certain addressing modes that you had in the 8086. And then you had some registers that dealt with how to do the addressing. So you sometimes needed to extend the address range beyond the amount of data that you could address. For example, with a 16-bit architecture, you couldn't reach enough virtual memory so you had more physical memory than you had virtual memory sometimes. And then you could use this segmented address registers to sort of offset your virtual address space into the large physical address space. So not very many general purpose registers and quite a lot of different addressing modes supported by special addressing registers. And we've already discussed this a little bit before. So the x86 instruction set is said to be a complex instruction set, and this is in contrast to the RISC, reduced instruction set computer, that became popular in the 80s. So the RISC, reduced instruction set computer, was sort of a load store architecture. So either you accessed memory using load restore, or you had an ALU instruction that only dealt with registers, but you never had a mixture of accessing memory and doing ALU instructions in the same instruction. Also, the RISC instructions only had, or almost only had, general purpose registers. So there was no special magic registers that was only used for some funny little address mode. And there also came a lot of simplification. For example, instead of introducing a special instruction that for when you needed the constant 0, instead it was by convention these RISC proposals said that whenever you try to read the register 0, we always going to return the value 0 to you. Just some minor simplifications in the instruction set. But the net result was that was a very simple, clean instruction set. So you could implement these kind of instruction sets very efficiently with few transistors, and that was important back in those days. x86 complex instruction set computer, on the other hand, it has ALU memory accesses sort of in the same instructions. So you can have an ALU instruction that takes one of its operands from a register, another operand from memory, and so on. So these are fairly complex instructions. There are lots of different esoteric addressing modes that almost nobody uses these days, especially not compilers. Compilers tend to like fairly simple addressing modes. It has very, some very specialized registers, as I said before, not just general purpose registers. It has variable instruction length, which makes it hard as well. So in the 80s, in the 90s, especially in the beginning of the 90s, x86 was a lagging performance compared with the RISC proposals, with the Alpha, the Spark, and so on. So what happened then is that the x86 designers started to rethink, and they came up with an internal implementation where you have an inner core that looks very much like a RISC implementation. So internally, the instructions that you execute at gigahertz are not the x86 instructions. It's a simplified instruction set. Maybe some of the simpler x86 instructions are included in this instruction set, but the more complex x86 instructions are not included in what is actually being implemented in the pipeline itself. And then you make a translation, and you do this dynamically in hardware from the complex instructions that are not included in the RISC-ish micro operations, is what they call the RISC-ish kind of instructions. So you translate from the more complex x86 into these RISC-ish kind of instructions, and from the time AMD and Intel started doing this, then there was no huge advantage from a performance point of view to implement RISC processors over these CISC processors. You just needed to implement this translation in hardware and add a little complexity, but we were already then at the transistor count where the number of transistors needed to make this translation was not that high, and also the extra latency for making this translation wasn't hurting all that much. To further overcome the overhead of these micro-ops, Intel introduced in Pentium 4 something called the trace cache. So after you translated the basic block once into these micro-operations, then you stored that translation in a cache, such that if you wanted to re-execute an instruction that was already translated, you could get this already translated basic block from the trace cache and avoid the need to continuously make the translation from x86 into these micro-ops. There was also this was also expanded to something called the loop cache in Core 2, and it's been expanded even more moving forward. Also, what happened pretty much at the same time was that the people implementing x86 and even more so their customers started to realize that 32 bits wasn't enough. So the ISA was extended, and this was actually done by AMD 2001 to a 32-bit, to a 64-bit instruction set, where they also took the advantage of this point in time to actually redefine some of the instructions a little bit and redefine the registers. So here we suddenly got a 64-bit virtual address space, so that's good. And we also had an opportunity, since we were re-engineering the instruction set a bit, you added new registers. You were still backwards compatible because the old registers still existed, but you introduced new registers R8 through R15. So this gives us like 16 more general purpose registers, so that was much better, much closer to what you have seen in the RISC processors before. But also, since this is a point in time when we started to move towards out-of-order execution, we also started to see the renaming of registers that you get from the Tumasulu algorithm. So effectively, the number of registers you had in the real implementation was much higher than these 16 registers. So that further took away some of the differences between RISC and CISC. We also started to see what's called more and more of the vector instructions. So in this generation, it was called SSE. Before the vector instructions, it was called MMX, and so on. So I'll talk a little more about vector instructions in the next slide. But in essence, it's a way of making use of the very wide floating point registers that started to have on chip, and actually take advantage of them to implement integer operations and even byte operations at a much higher rate. Still, this design was backwards compatible with x86. So there have been many names, many adoptions of this instruction set. So sometimes it's called IA32E. So IA32 is a 32-bit instruction set. EM64T is another name I've seen, or Intel 64. I should just warn you, though, that the term IA64 does not refer to x86 64 implementations in any way. It refers to the Itanium implementation, VLIW implementation that Intel also has done, and we'll talk about that in a couple of videos. So what is a trace cache? So a trace cache contains already translated micro-ops. So finally, we're going to talk about the vector instructions that we start to see more and more in x86 as well as in other implementations. So vector instructions, as I already said, they take advantage of the fact that we have floating point registers that are much wider than the normal integer registers. And when you have these wide registers, instead of saying you can only use these wide registers for floating point, you use the vector operations allow you to chop up one of these registers into several places where you can store data. So instead of having one long floating point operation, you can have maybe 4 integer data items stored here in one of these. And then there are certain instructions that can say, for example, load, vector load, or vector multiply. So in this example here, I'm referring with these vector loads and vector multiply and vector stores, I'm referring to these floating point or vector registers. And when you say vector load, register A, and then you identify some place in memory here, what that means is that you're going to load from that place in memory, you're going to load consecutively, load 4 values, not just one value. So one instruction loads 4 data items into these places. Of course, these data items has to be smaller than floating point units. And of course, load B also loads into this vector register here. And then you say vector multiply. Multiply A by B, store the result in D. What that implies is that you're going to do 4 multiplications in this example in parallel with a single instruction. So The instruction operates on multiple, a single instruction operates on multiple pieces of data at the same time. And you're going to store the 4 different results in the 4 places that's, or the vector locations, the 4 vector locations of vector register D here. So that's, and then of course you can store all these 4 values back to memory using a single instruction. So in some sense, what you do here is to make sure that you are leveraging some wide register storages, as well as, you can leverage some of the ALU implementations that already exist to allow us to operate on multiple integers or multiple bytes. You could do byte compare. So if you did bytes instead, you could take this, the vector A, and divide it into 4 times as many bytes maybe. So you would have 16 bytes. And you could do byte compare A with byte compare B, or you could ask the question, does any of these 16 bytes stored in vector A, is any of those equal to the ASCII A? So you can implement very quick searches and so on using those kind of instructions. So this has been going on for quite some time. So MMX was the first vector instruction set implemented by Intel, and then you came the SSC, and the difference here is just how many bits each vector has. So SSC went up to 128 bits, so you could do 4 32-bit integer operations like what I showed in the previous example, for example. AVX, which was released a couple of years ago as a new instruction set for the Sandy Bridge chips, has 256-bit vectors. And the Mike Xeon Phi, which was released about a year ago, almost exactly a year ago actually, at Supercomputing last year, it has 512-bit vectors, so you can do 16 32-bit integer operations in a single instruction. So which statement of these statements about vector instructions is true? So true statement is that it's a single instruction that operates on multiple data instances. And sometimes this is referred to as SIMD, single instruction, multiple data kind of parallel processors. We're also going to touch base on that later on in this course.